Hello everyone. In this short video, I'll show you I'll explain how to use the DWSIIM software to calculate an exit temperature for a stream in a heat exchanger. This example is related to a shell and tube heat exchanger, which is the most commonly used type of heat exchanger in industrial application. So what a heat exchanger is, it consists of two parts. It consists of a shell part and a tube part. So the specification of this type of heat exchanger depends on how many shell and how many tube passes do we have per shell. So when we do the detailed design of this heat exchanger, we need to know the internal diameter of the shell side, the length of the tubes, as well as how these tubes are arranged. They could be arranged in a rectangular or a square shapes. And as well as we need to know the diameter as well as the length and the fouling factors. Well, the main aim in the design of a heat exchanger is to calculate how much heat can be transferred from the hot to the cold fluid. So we need to calculate the amount of Q or heat transfer in the hot as well as in the cold fluid. And since it's an energy balance, both these values are equal to each other. So the amount of heat transfer from the hot fluid equals the mass flow rate times its heat capacity times the temperature difference, which is T out minus T in. The same thing goes for the hot one. The heat transferred from the hot fluid equals its mass flow rate times its heat capacity times the temperature difference. So this figure here shows a counter current heat exchanger where the fluid moves in the opposite direction. So those two equations come from thermodynamic principles. From heat transfer perspectives, the amount of Q equals the heat transfer coefficient, which is U times the surface area times the logarithmic mean temperature difference. The logarithmic mean temperature difference equals delta T1 minus delta T2 divided by the ln of delta T1 over delta T2. Now, the value of delta T1 equal the inlet temperature for the hot stream minus the inlet temperature for the cold stream divided the delta T2 equal the outlet temperature for the hot stream minus the outlet temperature for the cold stream. This applies for a co-current heat exchanger. So what the DWSIIM can do, you can do different things when it comes to the design of a heat exchanger. Basically, it can calculate the exit temperature for either the cold or the hot fluid, as well as we can obtain both temperatures. In this case, we need to provide the software with the exchange area and the overall heat transfer area. We can also use the DWSIIM to do a complex case in which we only know the inlet temperature for both streams. And we provide the DWSIIM with the geometrical specification of the heat exchanger. And it carries out a complex optimization procedure known as the Tinker method in order to calculate the amount of heat transfer, the overall heat transfer coefficient, and most importantly, the exit temperature. In a specific application, we need to use the heat exchanger as a vaporizer. And here we need to specify what is the vapor fraction in that stream. For example, in some cases, we would like to evaporate a certain fraction of hydrocarbons before they go to the distillation column. In this video, we will only solve this simple case. which is calculation of an exit temperature for one of the streams. In this example, it is required to heat 200 kilogram stream of air initially at 25 to 45. So this is the inlet temperature for the cold fluid. This is the desired temperature for the cold fluid. So we are heating it up from 25 to 45. 1000 kilogram, this is the mass flow rate for the hot fluid of air initially at 70 C. So this is the inlet temperature for the cold fluid, 70 C. I was given the surface area for the heat exchanger at 1 square meter. So what do we need to calculate in this case? We need to calculate the exit temperature for the air, which is the hot fluid. We need to calculate the exchanged area, Q, as well as the heat transfer coefficient, U. Let's go to the software. So this is the DWSIIM software. The first step is to open a steady state simulation window. This was the first step, and after that we need to choose the compound. You can either type their name or choose them. We only have air and water in our example. It's only air and water. So we have chosen water, air. You have to make sure that this tick, that you have ticked the box next to air. Next, the same thing, choose water, and then click next. Here we need to choose the thermodynamic package. It depends on how complex your system is. Since we only have air and water, we can choose one of the simplest ones, which is Raoult's law. So click on Raoult's law, click add, make sure it is added here, then click next. Then we have to choose the system of the unit. To make life easy, the system of the unit here has to be similar to what we have in the statement of the question. So in the statement of the question, I was given the mass flow rate in this unit, kilogram per hour. So you have to look for the system of the unit where the mass flow rate is given in this unit. So the first one, which is the default, is the SI. The mass flow rate in the SI system is kilogram per second, so it will not do. Of course, it's very easy to do the conversion, but we would like the unit to be similar to those one that we have in the question. Well, I know before that C5 give me the correct unit for the mass flow rate, which is kilogram per hour. So next we click finish. We choose a material stream. So choose a material stream and drag it on the software window. Choose another material stream. One of those material stream is for the cold. The other one is for the hot fluid. So this one, let's click on the first one and go to the stream conditions. In the stream condition, the inlet temperature for the cold stream is 25. I was not given any information on the pressure, so let's assume it's 1. The mass flow rate was 200 kilogram per hour. Next, go to the compounds amount, where we have the mole fraction or the mass fraction. So it doesn't matter actually, because the cold stream consists of pure water. So this is 1. And for the air, it is 0. Click enter, then accept, and change the name. This one is called inlet. Well, then close the window. Next, go to the second stream that you have added, and we know the initial temperature, it's 70. The pressure is 1 bar. The mass flow rate happens to be 1000. We need next to specify the mole fraction. It's purely air, so the mole fraction or the mass fraction of air is 1. For water is 0. Click accept, and change the name to hot inlet. Okay. Well, this is a counter current heat exchanger, so let's rotate this stream, the direction of this stream, so it looks nicer. Click on it, then go to rotate, then choose -80. Okay. So what do we need next? We need to add 2 streams for the exit of the cold fluid and exit for the hot fluid. So we need to choose another one. So let's choose it. This one, we only need to change the name, nothing else, because the software will calculate the specification. So this one is cold. And this one is the hot exit. Okay. Once again, let's change the direction of this one. So click on it, go to rotate, and -80. Next, we need to choose a heat exchanger from this list. So those are the heat exchanger. Choose the heat exchanger and drag it. Next, click on the heat exchanger, and let's do the connection. This is an important part of the simulation. So the inlet stream is the cold one. Inlet stream 1 is cold inlet. Its outlet, it's basically cold exit. Inlet stream 2, it is hot inlet, and its outlet, it's hot exit. Close this window and we will see the connections. So these are the connections now. All the connections are correct. Let's stop the solver. Click on this one. Next, click on the heat exchanger. Now we need to specify what do we need to do. So we would like to calculate the outlet temperature for the hot stream. So click on this one, which is calculate hot outlet temperature. There is no pressure drop. It depends on our assumptions. We know the cold fluid outlet temperature. It was 45 from the statement of the question, and we know the surface area, it was 1. So the software will now calculate the hot fluid outlet temperature, as well as the global heat transfer coefficient, the U value, and most importantly, the heat exchanged. So now let's enable the software. You can either click on F5 or click on this one. Okay, I think now everything is calculated, but we have to make sure that we have entered all the information correctly before. So this is the cold outlet temperature that we specified. This is our area, and now everything is calculated. So the temperature for the exit stream, for the hot exit stream is calculated to be 53. This is the optimized U value, 173, and this is the exchanged heat, which is 4.6. Now, if I would like to view everything in a table, you can go to Insert, click on Property Tables, and click here, choose the exit. These are all the properties that we can view. We are interested in the temperature. The mass flow rate doesn't change. Do the same for the cold inlet, choose the temperature. For the hot exit, choose the temperature. For the hot inlet, choose the temperature. Then close this one, and everything is given here. Okay, this is the exit temperature for the cold, which we have already specified before. This is the inlet temperature, which we know, and we have calculated the exit temperature for the hot fluid. It happens to be 53. But that's the end of this video, and in the next video we will cover 2 more cases, which is how to specify a certain fraction of an evaporated fraction, and how to do a rating of a heat exchanger. Thank you.